This is again a video on lossless compression coding, which is basically called, which offers very high order of compression, lossless, which I choose to call tree reduction coding, for want of a better word. You can say that this is the form of lossless compression coding which represents the lossless hacking of the virtual information tree in the virtual world by means of afforestation, as opposed to the lossy hacking of the real tree in the real world by deforestation. Now I perform this coding for the binary base alone, but you can see that even for this binary base it offers very high orders of compression. For larger bases it should offer better compression, and again you can see whatever variants you can do for this also. Now again our objective is to code a number which is 2 power L dash losslessly in a number which is 2 power L, where L dash is much greater than L and L dash is also greater than 1 here. We do not know how much greater L dash is to L. We will have to find that out. As yet we do not know as yet. So the information that needs to be coded is a 2 power L dash. So it is not, it can be represented as a tree, binary tree of height L dash. So you will have the first level, and then you will have here the second level, and so on up to L levels. Last one, this will be L dash level, sorry, L dash levels. Now the ratio associated with the first node, first level or the 0th level, height 1 is half. The next ratio for these two will be 1 by 4, and if we have 4 here, this ratio here at this level will be 1 by 8 and so on. So last one will be that ratio. So this is the information tree which needs to be coded. Now I'll take the same information tree only. As a preliminary example, I shall take only of height 4. So here I have 2 here. Now what I shall do is I shall encircle and enclose a tree of height 2 and make it into one node. Then since I would like to have a binary tree only, I shall now enclose a forest of 2 trees, subtrees of height 2, and I circle it and make it into one node. And then again 2 more here. So I have taken only height 4 here. So now what happens is, this is the information tree. Assume that this tree can be extended, and L dash is also enclosed. Last node also is enclosable. So now what happens here is, as we can see, the number of nodes here is initially for a height subtree. Now this is the smaller tree, but it encloses the larger tree. So here we can see that for the first level there is only one node. For the second level, each node there are two nodes, each of which is a forest of two nodes each. Now for the third level, it will be there will be four nodes, each of which will be a forest of four nodes each. So in general, you will see that the pattern is, this tree can be extended. The pattern is 1, 2, 4, 8 and so on, like this. For the second level, there will be a forest of two nodes, two trees of height 2. Now what happens if we, the same thing only, but now we encircle a tree of height 3 to form a single binary tree of height 3 to form a single node. Now what will happen here is, again this will be 1, but there will be 4 nodes here, a forest of 4 trees here, subtrees here, and a forest of 4 subtrees also here. So here the first level there will be only one tree, one subtree of height 3 within that node. The second one there will be 4, a forest of 4 subtrees and so on. So this will lead to the sequence, and the third level, you can imagine it will be 16. So that this will lead to the sequence 1, 4, 16, 64 and so on. Like that, if you increase the height number of, if you encircle and enclose the height of subtree of height 4 to form a single node in the smaller tree, the sequence will come out to be 1, 8, 64, 512 and so on. So these are the levels. This is 0th level, first level, second level, third level. So clearly now we can see that if we have a tree of height L dash, if we wish to maximize the compression ratio, as we will need L dash is equal to some n square. So the height of the subtree within the node of the inner node subtree is equal to the height of the outer subtree, inner subtree within the node is equal to the height of the outer subtree. Inner tree height must be equal to the outer tree height. So L is equal to. So now in the last level, you will have a forest of trees there. Given any information, you will always initially, if you code the largest smaller tree which encloses the larger tree, you will come to a leaf node there which is a forest of subtrees, and then you will have to only code the last level in that forest last. So initial code for A will be n. Now since each of this has n nodes, totally n square, 2 power n square nodes, that is L dash 2 power n square values and different values, but L dash tree of height L dash, the first initial length of the code will be n bits. The next length of this code will be square root of n bits. The third pass, third iteration to code that will be 4th root of n bits. And so basically L square, instead of n, if we take L dash will be equal to L square. So L square bits of information can be coded in L bits proportional to L bits of data. It will be less than 2 times L of, because it comes out to this, which is less. If it were n plus n by 2 plus n by 4, then it will come to 2n, but it is n square root of n, 4th root of n, and so on. It will come to less than 2n. So in general, it is L dash to L square to L lossless coding of information. Now here we have performed the coding only in a binary base. What happens if we extend the base of the coding? That is, you can have an n-ary tree where n greater than 2. So this should give, you could try doing that. What happens if you assume different bases for the information and different base for the code and so on? How do you go about doing that? So you can try out all these various versions of this and see what you can do. You can also slightly play around with it. So this is basically using trees for losslessly coding large amounts of information.